So today, a couple of things. We're going to talk about scientific notation. Then we'll talk about what scientific notation has to do with sig figs. And then we will talk about what to do with sig figs when there's multiple pieces of math. What do you do if you got both adding, subtracting, multiplying, dividing? And we'll see where that shows up as we talk about accuracy again. We're going to try to tie all these pieces together. Yeah. First part is the sales pitch. Okay, you learned scientific notation in your math class before and then never used it again. Okay, so scientific notation is just a way of dealing with really large and really small numbers, right? So to give you a sense of why we need to deal with really large and really small numbers, we'll talk about the kinds of things that we can expect to investigate in chemistry, and things you could easily see that you would need to do math with. Okay? So chemistry deals with very large and very small numbers. So this much water, 18 milliliters of water. Okay, water's H2O. H2O is a molecule, so it's made up of little tiny pieces of H2O. How many water molecules do you think there are in there? A lot. A million? Do you think there's a million in there? More? How about a billion? A trillion. Trillion sounds pretty big, doesn't it? Well, the actual answer is that. Okay. And there's million, there's billion, there's trillion, and you got 600 million of those trillion. That number is big. Can you see where we need that number? We're talking about individual molecules. Okay. And that's an idea, an example of the big number. Can't say it out loud. Discuss that number with your friend. Can you see the problem? You can't even say it out loud. Imagine typing it into your calculator. Could you have accidentally missed one of those zeros? No, you wouldn't miss one of those? Well, how about one of these? Because one electron has that mass. And this time there's 27 zeros in front of the 9. Say that out loud. You can't, right? There's just no way to. You can't discuss it. Do you want to try using your calculator to do math with that? Are you convinced that we need a shorter way to write these numbers? Okay, everybody convinced. There's my convincing. There's a reason why we're learning this. It's not some random thing. Okay, and then the way we're going to do it is scientific notation, or I like the official name, standard exponential form. The reason I like that name better is because it tells me something about it. Scientific notation just tells me who uses it. Standard exponential form tells me what it's like. Okay, standard. We are going to run into the word standard a few times this year. Standard means a group of people got together and said, this is the way we're going to do it. There's no reason in nature for doing it, but we're going to do it this way. That's what standard means. A group of people got together and said, this is the right way to do it. Okay? Exponential. Exponent. So a group of people got together and agreed to use exponents in their form of the number. Okay? So, two parts. First part. A number between 1 and 10. Can anybody think of a number between 1 and 10? 8. 8 is between 1 and 10. How many numbers are there between 1 and 10? Is 8.1 between 1 and 10? So once I say 8.1, that tells you how many numbers are there between 1 and 10? An infinite number of numbers between 1 and 10. Think number line, right? It's an infinite number between any two numbers. Ooh, scary. He used infinite. Okay. So what does that mean? Well, what do they all go? What do I mean by this? Well, I mean 1 is less than or equal to x, which is less than 10. So we include the 1, but not the 10. So that means that everything that is a number between 1 and 10, what it has in common is it starts with a digit, and then there's a decimal point. Starts with a non-zero, then there's a decimal point, and then there's stuff after the decimal point or not, it doesn't matter. That's a number between 1 and 10. That makes sense? One digit, decimal point, that tells you I'm between 1 and 10. Okay? And we're going to multiply it by 10 raised to some power. That's the exponent. The exponent is the power of 10. What you're going to raise 10 to? So that really huge number, instead of writing all this, I can write 6.02 times 10 to the 23rd. I turn it into a number between 1 and 10, 6.02. If I multiply that by 10 23 times, I'll get that answer. But I can say the bottom one. I can't say the top one. Okay? And that little tiny number, I can't discuss the mass of electron when I write it out, but I could say it once I turn it into scientific notation, 9.11 times 10 to the negative 28th grams. Should be a grams there. Forgot my unit. Okay, so this should be reminders for everybody. You learned them in math class once and then you never used them. Can you see why we have a need for them? If we want to add up how heavy an atom is, you've got to add that number. You want to try to line up decimal places? See how that could be a pain? Okay. So, quick reminder about how to get a number into scientific notation and out of scientific notation. Okay. Determine the number of times you have to move the decimal point to make it a number between 1 and 10. Because for every value, there's always exactly one place that you can put the decimal point that will get you a number between 1 and 10. So all you have to do is figure out how far you have to move it. And we're going to use a technique I call counting. So if I wanted to take 3,240,000 and write it in scientific notation, there is only one place in 3,240,000 that you can put a decimal point that will get you a number between 1 and 10. The only place I can put it is right there, between the 3 and the 2. That's where my decimal point I need to put it. Because that's the only place I can put it that'll give me a number between 1 and 10. Okay. Where does the decimal point start out? If you don't write a decimal point in, where is it? If they don't write a decimal point in, it's down here, right? It's at the end. So I would have to move it 1, 2, 3, 4, 5, 6 times. I moved it 6 times, and that's going to be my power of 10. Now, my question is, my power of 10, I got 2 possibilities. It could be positive 6 or negative 6. Which one do I use? I want a big number. If I multiply by 10 to the positive 6, I'm multiplying by a big number. If I multiply by 10 to the negative 6, that's a small number. Right? So, 3.24 times 10 to the 6th is the same as 3,240,000, just written shorter. Okay. And what if the number's smaller? Hey, I fight your math teacher on this one because your math teacher, when they taught it to you, I got odds they did left and right. They talked about moving the decimal point to the left and moving the decimal point to the right. I don't teach it that way. Here's why. Everybody in the room point to the right. Can you see why it would be hard for me to teach left and right? Because it's exactly backwards for me. I could only teach it to you if I had my back to you. And you don't want my back to you. It's not my good side. Okay? So what I use is bigger and smaller. I want the same size value, but I'm going to break it up into two parts. Okay? And if I make the number smaller by moving the decimal point, like I just did, 3,240,000 to 3.24, I made that number smaller. So that part got smaller, so the other part has to get bigger. If one part gets small, the other part gets big. I use big and small, not left and right. There's two parts. If you want the same value as one gets bigger, the other one has to get smaller. Make sense? I mean, we can show it as simple as if I got 4 times 4 equals 16, right? If I made this a 2 and still want it to be 16, the other one's got to be an 8. This part got smaller, that part got bigger. So I ended up with the same value. So the same thing works with scientific notation. One part gets smaller, the next part gets bigger. So how would I turn 0.00045, how would I turn 4,500 thousandths into scientific notation? Well, it's the same process. There's exactly one place I can put a decimal point that will give me a number between 1 and 10. Where is that spot? It's got to go between the 4 and the 5. I'd have to move it 1, 2, 3, 4 times to get it there. So I'm going to write the 4.5. And going from that number to 4.5, my number got bigger, so my exponent needs to get smaller. So it's not 4, it's negative 4. One part got big, the other part got small. See how big, small I think is easier than left, right. You got to memorize left, right. You just have to notice big and small. Right? This is all familiar stuff, right? I'm just reminding you. Okay, going back the other way, move the decimal point the same number as the exponent. You just have to decide which way you're going to move the decimal point. How are you going to decide which way to move the decimal point? Well, if your exponent is going to go to 0. If going to 0 makes your exponent bigger, then the number has to be smaller. If going to 0 makes your exponent smaller, then the number has to get bigger. It's the same rule. One part gets bigger, the other part has to get smaller. So we can end up at the same value. For example, one of the numbers we'll need this year is the speed of light. And the speed of light is 2.99 times 10 to the 8th meters per second. That's the speed of light. Okay. Write that as an ordinary number. Well, I got the 2.99, and now I'm going to start with my decimal point here. I have to move it how many times? 8. Okay, and I'm going from 8 to 0, so the exponent's getting smaller, so the number has to get bigger. So 1, 2, 3, 4, 5, 6, 7, 8. So that should be 299 million. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, I left one off. 9. Should be 299 million. Can't count. Really hard? Meters per second. So if you had 4.87 times 10 to the minus third grams, I want to change that. I'm going to start with the decimal point between the 4 and the 8. I have to move, I've changed the exponent from -3 to 0. So I got to move it 3 times. And I'm making the exponent bigger, so I have to make the number smaller. 1, 3. 2 zeros in front of that 487. Fresh reminders? Okay, now let's tie old knowledge with new knowledge. Scientific notation and sig figs fit together really nicely. So you saw a few examples when you counted the sig figs for Friday. There were a couple examples of scientific notation. Confused a couple of you, not very many, but most of you figured out, but you confused a couple. Okay, all non-zeros in scientific notation are significant. Well, heck, there's a set of words we don't need there. I don't need in scientific notation. All non-zeros are significant figures. Just because they happen to be in scientific notation doesn't change that. Okay. So if it doesn't have a zero, it's not a zero, it's going to be a significant figure. Okay. But let's think about let's think about where the zeros would go in scientific notation. Okay, so I got to start with one number and then things after the decimal point, right? Am I going to be able to put a 0 here in scientific notation? No, because it won't be between 1 and 10. Everybody agree? It won't be between 1 and 10. Can I put a 0 here? Scientific notation. Yeah. So I put a number in front, right? Would that be a significant figure? Could I put it there? Would it be a significant figure? If I put it there, would it be a significant figure? Yeah, it's at the end after the decimal point. Okay. Notice that no matter where I can put a 0, it's in a place that counts. So in scientific notation, it's going to be an ending 0. If it's an ending 0, it's got to be after the decimal point because it can't be before the decimal point because it's got to be between 1 and 10. Or it's got to be in between. In between automatically counts. So what you write in scientific notation, every digit's significant. The zeros and all the non-zeros and the zeros. If you wrote it in standard form, they're all significant. So how many significant figures in 1.20 times 10 to the third? Well, that 0 counts because at the end after the decimal point, right? So that has 3 sig figs. Well, how come I didn't write 1200? Because that would be, if I moved it 3 times, I get 1200. This one's a placeholder. This one's estimated. It looks like it's right on the line. It's got a line every 10th, and it looks like it's on the line. Or every 10, it looks like it's right on the line. So this ruler goes 1200, 1210, 1220, 1230, and it looks like it's right on the line. Does that make sense? It really is tied to a ruler. Okay? So sometimes you have to write it in scientific notation in order to get the correct sig figs. Every time you write it in scientific notation, those are all sig figs. But some numbers, like this, you are forced to write in scientific notation to make the 0 count. We mentioned that before. We talked about it from the other side. We talked about it from the sig fig side. Now we're talking about it from the scientific notation side. If If you wrote scientific notation, your zeros are going to count. Okay, tomorrow, I need you to bring your calculators so we can learn how to use our calculators to do these problems. Does that make sense? So bring your calculators. Because last period, I think only 2/3 had them, and I don't have quite that many to lend out. So something with the E, EXP, or 10 to the X button. One of those three. EE, EXP, or 10 to the X. Do not get multi-view. If you have multi-view, I can show you how to use it, but it's a little tough. Okay. All right, so let's talk a little about more complex math with sig figs, rather than just adding, subtracting, multiplying, dividing. What about raising to a power? What if I got a square and I measured one side of it as 2.5? And I know it's a square. So 2.5 times 2.5. My calculator is going to give me more numbers he's going to give me 4 digits when I do that. How many do I get to write down? Oh, it's going to be 3. It's going to give me, I used to know 2.5 off the top of my head. Huh. All right. What are you going to do with those numbers? You're going to take 2.5 times 2.5, right? If it was a cube, you do 2.5 times 2.5 times 2.5. Raising to a power is just multiplication. Isn't it? So it's going to be the fewest sig figs in the problem, like multiplication is. Just like multiplication, so that's one more complex math that's easy to fix. If they ask you to cube something, it's just like if it has 4 sig figs, you're going to multiply 4 sig figs times 4 sig figs times 4 sig figs. So you're going to round off to 4 sig figs. Okay? If it's all multiplication and division, round at the very end. Because the rule is the same for multiplication and division. All I got to do is count how many sig figs there are in everything. So it's all multiplication and division. Type it all in my calculator, get an answer on my screen, and then round once at the end. If it's all addition and subtraction, it's all where they line up. You're going to have to line them all up anyway. Don't round twice. Round once at the end. The problem comes when you have both addition, subtraction, and multiplication and division in the same problem. Addition to subtraction means I count sig figs, or I mean I line up decimal places. Multiplication division says I count sig figs. Which do I do? Line them up or count them? So if you have addition and multiplication in the same problem, or subtraction and division, or subtraction and multiplication, well, you have to do the math right. And the math is PEMDAS, or PEDMAS, depending on who your math teacher was. Parentheses first, exponents second, multiplication, division in the same order, and addition and subtraction in the same order. So since multiplication and division fit in the same order, you can do them all at once. No pass. All right. So what do? You follow PEMDAS, and when you change rules, when you stop multiplying and start adding, you round according to the multiplication rules before you add. When you stop subtracting and start dividing, you round off according to subtraction rules, then you divide. You do, when you change rules, you stop and round. You want to round as few times as possible, but every time you change rules, you need to stop and round. Does that make sense? Yeah. And once you've rounded, you move on to the next operation. And when you change rules again, you stop and round again. And when you stop changing rules, you're at the end of the problem. So you got one last rounding to do. So every time you get to the end of the problem, you round, or when you change types of rounding rules. As long as you're following the same rules, you keep everything lined up, you're okay. Or you got the same number of sig figs, okay. So, .60 cubed. Yeah. But I got my calculator out so I can push those buttons, and I get 175.616. Okay. How many sig figs can I have in my answer? Well, the 560 has 3. And what I did was 3 sig figs times 3 times 3 sig figs times 3 sig figs gives me 3 sig figs in my answer. So the third sig fig is the 5. Behind that 5, there's a 6. So that's 176. Anything different there? So 273.25 grams divided by 75.1 milliliters minus 9.2 milliliters. What does that equal? If you push the buttons on your calculator is going to get you 4.146433991. There. Grams on top, milliliters on the bottom. Probably can't justify that many digits. So, how many sig figs do I write? Well, this has got 2, this has got 3, and that has got 5. So you're tempted to do 2. And if you did that, you'd get the wrong answer. Because I got 2 math operations here. This one's subtraction, and then I got division. Which rules, if I said that had 2 sig figs, that means I'm following the division rule. Right? Why the division rule? Why not the subtraction rule? Actually, the answer is we should do both. So you should take that 273.25 grams and divide it by 75.1 minus 9.2 is 66.9 milliliters. No, 65.9? 65.9. Okay. Now, what about sig figs in that subtraction? I don't worry about how many there are. I worry about where they're at. Okay? They both have 1 decimal place. So my answer should have 1 decimal place. So I need that 0.9. The 0.9 stays. Now I'm ready to do the division. 273 divided by 65.9 gets me 4.14. Oops, I forgot the 2.5. So it's 4.146, which is 4.15. Yeah. And that's grams over milliliters because they didn't cancel each other out. So see how you can be misled. You're tempted to say, hey, that has 2 sig figs. My answer should only have 2. But when I used that 9.2, I wasn't counting how many sig figs. I was looking where they lined up. Right? So when you change rules, stop it around. Make sense? Okay. Let me show you the error of my ways. Oh, of your ways. What's an error? Something's wrong. So as scientists, error is how wrong you were, right? Fair is how wrong you were correct. Don't want to say right. So we're going to start off with, in order to know how wrong I was, I have to know the right answer. The right answer is called the accepted value. We can't call it the right answer because the best thing we can do is it's the accepted value is based on reliable evidence references. It's the best we can do. Your textbook is one of your reliable references. When you're using the internet, check the site to see if it's reliable. See who wrote it, for what purpose, who they are. Yeah. That's the right answer, and then you're going to have what you get in the lab, and that's called the experimental value. What you get when you measure it. So how would you use those two numbers to figure out how wrong you were, what your error was? Subtract. Experimental value minus accepted value. That's how wrong you were. But notice it doesn't just say the difference, it puts it in an order. Okay? This can be a negative number. How would you get a negative number doing that math? The accepted value is higher than what you got, right? I'm subtracting a too big a number. So that means that your answer was too low. Positive would mean that your answer is too high. Now, if you had an answer that was off by 2 grams, did you do a good lab or a bad lab? Was your accuracy good or bad? You're off by 2 grams. Yeah, see, it matters what the correct answer is. Because if you're off by 2 grams out of 4, that's a 50%. You're off by 2 out of 4, you're half off, right? But if you're off 2 grams out of 2 million, you got a little tiny error. So error by itself doesn't tell us very much. We need to compare it to the right value. And that is called percent error. So percent error is the experimental value minus the accepted value divided by that quantity divided by the accepted value times 100%. Hey, look, we got subtraction, division, and multiplication all in the same problem. We might have to do complex sig figs. Okay. This 100% is a definition. That means it's got unlimited sig figs, so it won't affect the sig figs at all. It's exactly 100. It's 100.00000. Okay? So, hey, we can shorten this down a little bit because we have seen experimental value minus accepted value before. Look up 2 lines. This was called error. What's on top is error, right? If you put error over the accepted value, that's your percent error. How wrong you were over the right answer. And the sign's important again. If I get a positive error, that means my subtraction was positive, which means my experimental value was higher than my accepted value, that my experimental value was too high. That's how I'm going to get a positive number. If experimental value is big. And I'll get a negative answer if the experimental value is low, because I'll subtract a bigger number from a smaller number, get a negative number. So, what if I know I weigh 150 kilograms? Then I weigh myself and the balance says I weigh 165 kilograms. What's the percent error? Well, there's the equation. Percent error equals experimental value. Which one of those is the experimental value? I weigh myself on the balance. That's the experiment, 165 kilograms. Minus the accepted value, 150 kilograms, divided by the accepted value, 150 kilograms, times 100%, equals. Okay. Anybody think about sig figs while you're doing this? Because first I have to subtract, then I have to divide. So I have to follow both rules. So I do that subtraction. 165 kilograms minus 150 kilograms gives me 15 kilograms. Last sig fig in 165 is the 5. Last sig fig in the 150 is the 5. That 0 doesn't count. So I need to round this off to the tens place. That's 20 kilograms. Everybody okay with me so far? So now I have 20 kilograms divided by the 150 kilograms times 100%. So 20 divided by 150 equals times 100. Okay, the 20 has how many sig figs? 1. The 150 has 2, and the 100 has unlimited. It's a definition. So 1, 2, and unlimited, the smallest number is 1. So instead of the 13% of my calculator, I write 10%. Everybody okay with that? So yeah, we put those two pieces together. You guys didn't think about sig figs when you subtracted first. You push the buttons in your calculator. Okay, remember, you got to stop and think. When I change from that subtraction problem to that division problem, I need to stop and round. Okay, student measures the mass of a pencil. He finds that it's 25 grams. The actual mass is 22 grams. What is the student's percent error? So it's experimental minus actual over actual times 100%. So the experimental value When he measured it, he found it was 25 grams minus the actual, which was 22 grams, divided by the actual, which was 22 grams, times 100%. 25 minus 22 is 3 grams. What about sig figs there? That's the right sig figs, because 25 grams minus 22 grams is 3 grams, and they're both at the ones place. Divided by the 22 grams times 100%. 3 divided by 22. Calculator fills up times 100. Calculator fills up with numbers. How many sig figs in my answer? Well, the 3 has 1 sig fig and the 22 has 2, and the 100 has unlimited, so I can only have 1 sig fig, which makes it, again, 10%. When we write down 10%, that means someplace above 0 and less than 20. Right? We're not sure that's really a 1. Make sense? Really complicated? Okay, so these pieces fit together. They're not separate pieces that we do this here and this here and this there. Tomorrow we get our calculators, we'll deal with scientific notation in your calculator and how that messes up rounding. Okay? And then we'll start on the other half of these pieces, which is the grams, to talk about the metric system. But tonight you're going to do Reading Guide 2.2. That is the second side. You did it out of order. You did 2.3 first. Then you did 2. I need you to do 2.2 now. Okay. You okay at that? All right.